Hello everyone. Our capstone project is automated gait cycle signal detection. We are working with UBC Faculty of Medicine, the Motion Analysis and Biofeedback Laboratory to develop a MATLAB code which will accurately identify gait cycles from IMU sensor data situated in a wearable device. What is gait? Gait in humans is described as movement of the human limbs involving the complete body. The cycle is a pattern of steps and strides, which is identified through a series of phases. To keep it simple, we will identify 4 phases of a gait cycle: the push-off, the swing, the heel strike, and the stance phase. These phases together form the cycle of a gait. The foot progression angle, which we acronym FPA, is the main identifying criteria for this project. The FPA is defined as the angle between the line from the heel bone to the second metatarsal, which is shown in the diagram as a foot vector, and the line of progression averaging from heel strike to toe off during the stance phase of walking for each step. This is identified as the heading vector. The angle between these two vectors is the FPA.
The lab has developed a wearable sensor shown in the picture to calculate the foot progression angle, which can be found without the patient being in the lab. Our goal is to use the data from the sensor to develop algorithms to differentiate linear walking that we classify as good steps from nonlinear walking classified as bad steps. The key performance outcomes are as follows: identify good steps versus bad data, develop algorithm to evaluate types of steps, if time permitting, eliminate errors induced by the sensor such as magnetic interference.
One of the most promising algorithms we found in our literature review was a paper by Wang in 2012. In this paper, they created an algorithm where you could input a gait signal and the algorithm would output which phase of the gait cycle, stance, push-off, swing, or heel strike, each sample was in. Finally, they were able to classify whether the cycle showed someone walking up the stairs, on level ground, or downstairs using information of time spent in each phase of the gait cycle. Now we will go over the algorithm and how we implemented it. We used two features in our algorithm: SVM, the magnitude of the resultant acceleration vector, and SMS, which is SVM minus the acceleration in the y. The n denotes the sample number. Our first objective is to find the samples in which the person is in the static phase of the gait cycle. Since we are using standard deviations and means in our algorithm, we first window the data to attenuate for any baseline drift. Then we go through and find the mean and standard deviation of SMS in each window. Then we create a band of permissible SMS values governed by two standard deviations from the mean. If the value of SMS falls outside this permissible band, we set it to 0. We use this filtered data and recalculate the mean and standard deviation. If the value of the filtered SMS falls in one standard deviation of the mean, we classify it as a static candidate. There is a limit to how fast a human can move in the literature by Chai in 2012. As such, we remove candidates if they are not in the static phase for at least 0.3 seconds. So here are results from the objective one. Orange is the classifier detecting whether or not it's in static phase or non-static phase. If it's static, orange is 1, and if it's non-static, orange is 0. The blue signal is the accelerometer's Z rating. As you can see, when the duty cycle of the orange pulses is relatively stable, the blue signal shows a periodic gait cycle. When the blue signal is periodic, we have good steps. In order for it to be a complete gait cycle, it must have a static phase and the 3 dynamic phases: push-off, swing, and heel strike. The rising edges of the orange gait signal define a gait cycle. We must now find which dynamic phase the gait cycle is in for each of the samples which have an orange value of 0, or non-static. We create DTJ. Here J is the cycle number, K is the sample in each cycle. This parameter DTJ is calculated for each cycle, and when the criteria is true, we switch from push-off into swing. When DTJ is equal to the acceleration in the z-axis the second time, we switch from swing into heel strike. Here we have the classification performance of the gait cycles phases from the original paper. On the right, we now have our algorithm's performance of classification of the gait cycles. The green line is the value of the accelerometer in the z-axis. The blue line is the classification. 1 is static, 2 is push-off, 3 is swing, and 4 is heel strike. Push-off is classified as too short when compared to the original paper, but this can be fixed by tweaking the standard deviation of 1 in objective 1. Overall, we were able to reproduce the results of the original paper, and our results are very promising. Foot projection angle only matters when a step occurs. On the right, the microcontroller is filling our data with bad foot projection angles because the person isn't moving, but it thinks thinks the person is taking a step. We ran our algorithm on the noise data and removed all the cycles that don't have one sample in state 4 or heel strike. After running through this filter, the results are shown on the left. We only had 4 detected steps. If we zoom in on one of these noise steps, we are only in state 2 push off for only 10 milliseconds. It's impossible for a person to move this fast. As such, if we add more filters for the minimum time in each phase, we can remove these remaining noise steps as well.
Moving forward, we will continue with SVM algorithm and investigate the acceptable amount of time for each gait cycle and eliminate any steps that is out of range. We will then validate the algorithm by collecting good and bad steps from multiple patients and comparing the accuracy of the classification.